Hey, hello, welcome back to my YouTube channel. It's Ranjan, and it's been a couple of months I have not uploaded any video. I was aligned somewhere else in my office. So now I'm back with another video in which I will be showing you implementation of basic GAN using Python. So basically GAN is Generative Adversarial Network, and I have already uploaded a video about the GAN, how GAN works, what are the practical application and what is the architecture and where else we can use. If you have not watched what is GAN or you're not aware about the GAN, so this video won't be any help to you. So first I will suggest just search GAN by Ranjan Sharma. So you will see this video that I have uploaded. In this video, if you will see, like, I have covered each and everything how GAN works and what are the architecture. And so basically, if you are not aware about the GAN, I will tell you about that thing. So there in GAN there are two things. First is generator and second is discriminator. So generator will try generate each and every sample, and generator is not aware about what needs to be generated. It will generate any random sample. So let's take example of image. It will create sample of the images each and every time, and discriminator will identify whether the image generated by you is legitimate or not, is real or not. When discriminator will give its feedback that this is not real, so generator will combine that feedback and it will generate new image. So it will try to generate, it will keep on generating new images and images, so till the time discriminator will say that this image is real, so it will keep on generating. So this is example. Generator will try image and it will be of fake data, so fake data would go in discriminator and discriminator know about the real data, what is the real data. So on the basis of these things it will identify whether the image is real or not. If it is not real, so it will give the feedback to the generator, and it has many industrial application I have covered in this video. There are many applications there. This is a website that I have showed you in this video. By using GAN, we can create so many images in any example, in any scenarios. So in this, I have shown you that GAN can generate so many face images which does not exist in reality. This person does not exist in reality. So this is just an image which is generated by a GAN. So in this video, I will show you how our GAN model will create a images. And in this example, I am just taking a example of Mnist dataset. And if you all involved in data and machine learning, so you must be aware about what is Mnist dataset. So Mnist dataset is just a collections of the handwritten digits. So it is just look like this. So there are two things. First is generator and second is discriminator. So I will train my discriminator that what are the real images look like. But I will not train generator with those images. My generator will create random images by using some noise. So that noise is completely random. So it will keep on generating new and new images, and our discriminator will identify whether those images are real or not. So I have taken a basic example of MNIST because this GAN model will takes a huge computational resources. You must not be having GPU. I am doing this implementation on the collab. So first I will show you what are the steps that I will take. First I will import all the libraries, TensorFlow, all the libraries which are required to create a neural network. Then I will get ready my MNIST datasets which I will download from the internet. And after that I will do some pre-processing this data set. I will do scaling or flattening or reshaping the data in the required format. Then I will define the function generator and discriminator. And then I will create some random noise and convert this random noise into image. And then I will compile my discriminator, and this would be generator. This would be generator. Okay, so I will compile my discriminator and my compile model of generator. Why generator is combined? Because in generator I will feed two things. First, the random data, and second thing, feedback from the discriminator that I have shown you in the last video of the GAN. So discriminator would be alone and generator would be combination of two things. First, the random noise, and second is feedback from the discriminator. Then I will set the parameter, what are the epochs, what are the loops, how many loops need to be run, and what would be the batch size, what would be the sample size. Then I would define the function which will create sample images. Here I have defined the generator and discriminator, but in the generator I have to call these functions because this function will create or generate the images. Then I will do training of our discriminator, then our generator. So it will create images. Then at the last, we will see what are the clarity of the images that are generated by the generator. So I have shown you all the steps that I will be doing in my collab notebook. So let's start the implementation. So first of all, we have to change the runtime as GPU. I have already done that. You would be seeing that it has none, but first of all, we have to change to GPU so that we can use the GPU resources while implementing our code. So in this, I will be installing the TensorFlow with GPU module, and I will be using TensorFlow 2 version. So now I am importing all the libraries. So this is the Keras module inside the TensorFlow in which I will call input dense leaky ReLU. Leaky ReLU is the activation function, and this is batch normalization. So leaky ReLU and batch normalization is very important or very popular in terms of GAN. And batch normalization is a technique by which we can train our deep neural networks, and it will just normalize our inputs to each layer for each mini batch. So batch normalization is altogether a different topic I will be covering in next video. But as of now, you can take example like whenever we have a deep neural network with so many layers. So in that layers, it is very challenging because in the middle layers, it could be very sensitive to a initial random weight. So by using batch normalization, we will just normalize or standardize the input that we will be giving to each layers. So next I will be calling model, and in this I will be importing some optimizers that Adam and SGD. I will not be using SGD here, and these are the basic libraries. And in this I am just downloading the Mnist dataset from the Mnist. I am just saving that data in the xtrain xtest, and I am scaling my data, my input between -1 to 1, so that our image pixels would be sensitive around 0. So what I'm doing here, just dividing by 255 for all data, and these are the images. So you must be aware of like how images looks. So images are the numbers which start from 0 to 255. So I'm just dividing first by 255. So if I will divide my images by 255, it will be in between 0 to 1. So then I'm multiplying by 2 and subtracting by 1. So this is just to do scaling so that our data would be in between -1 to +1. So I will check the shape. So I have 60,000 images in the X-train and 10,000 in the X-test. And the pixels are 28 by 28. So this is the length and width. So first I am flattening my data to just bring the data in the tabular form. So this is my number, and this is my height, this is my width. So and here my dimensions would be 28 into 28, and I am reshaping my data. So reshaping my data to dimensions, which would be this. After reshaping, my data would be like 60,000 into 784. So I have reshaped my data, which was my Mnist data set. And this is the latent dim, which would be dimension of our latent space. So that would be the number of the inputs that we will be giving to the generator. So we can play with this hyperparameter. You can do tuning whatever you want. And here I am defining my generator function, and here I am defining my discriminator function. So in this I am giving my input that would be latent dim. So I will be defining the number of the layers. So first would be input, second would be dense layer, in which I am defining 256 neurons and using activation function leaky ReLU, and alpha 0.2, it would be another hyperparameter learning rate, so we can do any tuning for this. And then I'm using batch normalization, that I have already explained what is batch normalization. So this is the one input, then dense, then batch normalization, then dense, then batch normalization, then dense, and after would be dense layer, which in which I am using activation function 10h. I'm using a 10 function because our image pixel would be in between -1 to 1. So I have to use 10h function. And then I am using my model, which I have called here, this model. So in model, I am giving my I and X. So I input and X is another layer. So it will be returning model only. So here till that point, I have not called or compiled my generator function. I have just defined a function of generator in which it will return a model. So same scenario with the discriminator. So here I am giving the image size. So whatever the image that we will be providing to discriminator to train the discriminator. So first layer would be input, that would be equal to image size, and then I am defining the dense. There is no requirement of the batch normalization in discriminator. So here I am defining the learning rate 0.2 and using leaky ReLU as the activation function. And in the last layer, neuron would be single because it would be output. Well, it would be a binary classification, 0 or 1, whether the image looks like a real or not. And that's why I'm using a sigmoid function. It's a binary function. It will give me output 0 or 1. So same scenario, I am just returning the model in this. Now I am compiling both models, discriminator and the generator. So first I will define the D. So this would be a dimensions. Let me run this. So here I am using the dimension because it's a discriminator. So in discriminator, we will be giving our images to train the discriminator. So this D is a dimension. And here I am compiling with the loss binary cross entropy and optimizer is Adam and learning rate. I'm defining these and we can obviously play with this hyperparameters and matrix. I'm using accuracy here. If you will see in this, I am just compiling discriminator only. I am not compiling generator. Here I have used generator and but yes, I have given my input as a latent dim which I have used 100 in the above example, but I am not compiling generator here because I have already explained you in this PPT when I was showing you steps that in case of generator I will be use combination of the model. So I will show you in the next step. First, we will see the summary, how our model looks like. So in the generator, I have used these many layers. One input layer, dense layer, then batch normalization, and and another is discriminator. So it would be like this. So now it's time to create a noise from latent space. So latent dem we have used 100. So we are creating a noise which we will be giving to the generator. So first I have created the Z. So if you will see the shape, it is just like a with the 100 dimensions. But now we have to convert this Z into image. So I am defining my generator function which will create a image. So I am giving input as a Z which was noise. So on the basis of this thing, it has given me a image. It will be a just a random image and nothing would be there. Second thing, I don't want my discriminator to train. So first I have to train my generator. So I am setting the discriminator dot trainable equal to false. I want that only my generator would be trained in the first step. That image I have generated here. This image I will be passing to discriminator. So discriminator will tell whether that image is real or fake. So whatever the result, it will get stored into the fake prediction because the image we have provided to the discriminator is fake. So now at this point, I am creating new model which would be combined model. I have already created a model of discriminator. So now it's time to create the model of generator. So in this generator model, I am using two things. First is random noise. Second thing is the feedback from the discriminator. So this would be my combined model. So now I will compile this combined model. So I'm using compile model generator dot compile and same I'm using loss as a binary cross entropy and optimizer as a Adam and these are the learning rates. So my both model are combined. So now it's time to train our model. So to train the model, first I will define some configuration, basic configuration. What are the batch size that I will take? So batch size I am defining 32. We can take any batch size and epochs I am giving as a 30,000. Yeah, obviously we can use any number. So like number of the epochs would be increased, so we would be getting a good accuracy and we can play with that thing. And sample period 200. So that 200 is that after how many steps that our generator will create a sample. So like first epochs will be starting from the zero. So at the 200 epochs, it will create a sample. So it will create a bunch of images that we will define. So that I'm defining 200. So you will see like after 200 steps, it will create a image. So and we would be needing some labels ones or zeros whether the result is true or false. So it would be best to create them before we start training, so not to have instantiate new objects later on inside a loop function. So we create a set of ones and zeros. So basically it would be create according to a batch size that we have defined. So that was 32. So it will create matrix of ones and zeros and then we create to list, so to store the our generator and discriminator loss in each step or in each epoch. So next thing we will create a folder inside this Google Drive or Google Colab. So in this folder, it will store our images that our generator will create or generate those images. So it will be stored in this folder. So now it's time to create a function which will generate the images inside our generator function. So this is nothing, it is just a function which will create or generate a images on some epochs. So first I will define like how our images will look like. So I am defining rows and columns. So on one images, it will generate 5 rows and 5 columns. So in one page, it will generate 25 images. And here I am using noise. So I'm generating random noise vector that is from the latent space that we have defined 100, and then it will create a images by using function generator.predict, and I'm defining the noise here. So I will rescale the images between 0 to 1, and in this I am defining the figure and axis will be used to store the images, figure will be used to plot the images. And here I am defining index as 0, so because it would be a nested loop, and this loop will run till the 25, because 5 into 5 25, so it will generate the 25 images. So that's why I'm using a loop here. So it will run till 25 only. So what it will do, so it will just show the image, and it would use index, so it will create 25 images, and images would be of shape, height and width that we have already defined, that 28 into 28, and the images would be in grayscale. So I am using off axis here because I don't want to see the axis in the images, and it would increment index as a 1. Then it will save the images in the GAN images folder. It will store as a epoch number. So here would be epoch number. So whatever the epoch is running, so it will store the image with the epoch number, and then it will close the resources. So I have defined the function. So now it's time to train generator and discriminator. So first I will train my discriminator, and you must be knowing that in discriminator it will need real images and the fake images, because on the basis of those two things it will identify whether the image you have generated by generator is real or not. So in this I will give Mnist dataset in on which it will be trained. So it will select a random batch of images from the X-train. So X-train is my collection of the Mnist dataset images. All the images will be stored into the real images. And now it's time to generate the fake images. So it will create a random noise by using the latent dimension that I have defined as 100, and batch size would be 32. So on the basis of these things, I will use generator to generate the images, and that would be stored into the fake images. So now it's time to train the model. So I am using discriminator.train on batch with the input as a real images and the one factor which is used to denote that it belongs to positive class, because it these are the real images, and on the basis of these things we will get the loss and we will get the accuracy. And next I will use discriminator.train on batch with the input as a fake images and the zeros factor to just denote that it belongs to a negative class. Once I will run these things, I will be getting real and the fake loss and the real and the fake accuracy. So I will taking the mean of both things. So I will receive my discriminator loss and discriminator accuracy. So now I will train my generator model. So first I will create some noise, and then I will use my combined model, because in generator I have created my combined model. So in combined model I will use train on batch, and in this I am giving noise as an input. And once the trick is that we are trying to fool the discriminator is to thinking that images are the from the generator are the real. That's why we are defining as a once here. We can ignore this because the same thing. Yeah. And now it will save the losses, because at each epoch it will be generating the losses. At each epoch it will be generating the losses, and I will be saving those losses in the d loss list and the g loss list. And at the last point, this function I am using just to create a sample of images. And in this step what I am doing, if the epoch is the multiplication of the 100, so it will create the images and it will print some information, so at which epoch it is and what are the epochs are left, and it will create the generator loss and discriminator loss. And if that epoch is a multiplication of the 200 that we have used our sample period. So if that epoch is a multiplication of 200, so it will call the functions of the sample images, and this is a function in which it will generate a images. So now I will run this. It will take some time because I have defined 30,000 epochs here. So I will fast forward this video. So let this notebook takes its time. So as we can see, our 30,000 epochs got completed. So it took almost 30 minutes. And if you have the time, you can run for the 30,000 epochs. Otherwise, you can run for 10,000. I ran for 30,000 to just see like how accuracy is getting improved. So now I will plot the losses, discriminator and generator losses. If you will see, after the first few iterations, here from this point we can see that both losses, generator losses and discriminator losses, just hover around the same point. Blue one is generator and orange one is discriminator. So you can see that after a few iterations. So this is the case, like both discriminator and generating are getting improved during this time, and these losses should remain relatively the same throughout the training process, because ultimately generator and discriminator are feeding off to each other as expected. So we can see the bunch of the png files with the epoch number as the file name, so it generated for after each 200 steps. So first I will see the first image, which is zeroth image. If you will see, that image is completely noise. This is the starting of the training and we didn't see anything at all. There is no information visible. But if you will see, like after the 1000 epoch, so we can see something, some information is there. So as it will go increasing, like now I will see for 5000, we can put any number here, suppose 4000. So at 10,000, the information will be more visible because at this point our generator is more trained. So at 20,000, and this is at the 29,000. If you will see, even at this point 20,000 epochs, we are getting more information. So there is no need to go till 30,000. Even if you will see, like at 10,000 epoch, my information is still visible, but it's not visible at completely, so we can go till 15,000 epoch. So it depends on us. So I will say, moral of the story, that our generator is become intelligent and become learned and trained to generate real looking digits, and all credit goes to both discriminator and generator. So that's all in this particular video, and I hope I am able to explain you this topic with good clarity. If you really think this video is more of good explanation, so I am expecting your feedback and your like on this video. For any suggestion, doubts, feel free to let me know by posting the comment. Your such gestures really keeps me motivated to upload videos more frequently. So do share this video with your friends and colleagues. So don't forget to press the bell icon to get the notifications of my latest videos in your inbox. So see you all in the next video. Till then, goodbye, enjoy, happy learning, keep rocking.